We have some really great speakers today. As I mentioned, two of our guest speakers are with FrX. Drew Baird currently is a senior geologist with FrX with more than 20 years experience in remedial design and implementation, project and team management. He leads the company's business development efforts and provides technical support. Drew earned his bachelor's and master's in geology and is a registered professional geologist in South Carolina. Chapman is the director of technology with FrX. He also has 20 years experience in the environmental industry and is focused on in-situ remediation design and innovative technology development. He's a technical expert in injection methods and has led design remediation projects utilizing a wide range of treatment technologies. Chapman has a bachelor's degree in civil engineering and a master's in environmental engineering and science, both from Clemson University. He is a professional engineer in Massachusetts. Dr. Brant Smith is the technology manager at FrX, soon to be Evonik, with over 20 years of experience. Dr. Smith has designed and implemented numerous field applications and bench scale tests involving a wide range of treatment technologies and is our in-house expert on all things chemical oxidation. Brant has a bachelor's of science in civil and environmental engineering and economics and a master's of science and PhD in civil engineering from Washington State. He's a registered professional engineer in Washington State as well. Now I'll turn it over to Brant to get us started.
Thanks, Jen. I'm going to kick off this webinar, and then as Jen noted, it's going to include Drew Baird and Chapman, and we're going to be talking to you today about the application of Klozur KP slurry injection via hydraulic fracturing, some of the fundamentals, methods, and lessons that have been learned over the past, 5 years. Klozur KP was first announced in 2016. Okay, so I will be talking to you a little bit about Klozur KP Chemistry. I'll present some very brief Klozur KP case studies. Then I'm going to be talking to you about why Klozur KP, why KP or potassium persulfate versus sodium persulfate that has historically been used. And then I will be talking about some of the lessons that I've learned over the past 5 years in watching people apply Klozur KP. After that, I'll be turning this presentation over to FrX, who will talk about the application of or their experiences in applying Klozur KP over the last 5 years. First, there are two primary persulfates that are sold into the environmental market, and that is sodium persulfate or Klozur SP and potassium persulfate or Klozur KP. There's two real differences in these compounds. First is going to be the solubility. If you look at the table in the top right, you can see that from 0 to 25 degrees C, Klozur SP has a solubility of 480 grams per liter up to 580 grams per liter. In the same temperature range, you can see Klozur KP has a solubility of 17 to 59 grams per liter, or over an order of magnitude lower at most temperatures. For the environmental remediation market, many of our applications are between 10 and 20 degrees C, and you can see that Klozur KP has a maximum theoretical solubility of between 29 and 47 degrees, or 47 grams per liter in this range. The other primary difference is, of course, the residual cation, the sodium versus potassium, which may not mean much to every market, but there are a couple of instances where there are remedial goals on sodium, and thus adding a product that has potassium as a residual is favorable. Both Klozur KP and Klozur SP dissolve to form and release the persulfate anion. The persulfate anion is a strong oxidant. It can be activated to form a variety of oxidative and reductive radicals. Because these radicals are formed during activation, you can treat a very broad range of contaminants of concern with using sodium persulfate or potassium persulfate. Once dissolved, the persulfate anion tends to persist in the subsurface on the order of weeks to months. We typically say 2 to 8 weeks, with little to no gas evolution. Because you can get the oxidative and reductive pathway with the proper activation method of the persulfate anion, you can actually treat a very wide range of contaminants of concern. Most people, when they're thinking about ISCO, they think about the oxidative pathway only in treating things like petroleum hydrocarbons, MGP residuals, BTEX, PAHs, oxygenates, and 1,4-dioxane. Also, of course, you can, other compounds are treated by either pathway, the oxidative or reductive. And that includes your chlorinated ethines, chlorobenzenes, chlorophenols, these types of compounds. But in addition, there are compounds that typically need the reductive pathway that can be treated using something like alkaline hydrogen peroxide or heat activated persulfate. And these include carbon tetrachloride, 1,1,1-TCA, dichloroethanes. Some of these compounds, such as DCAs, do have a weak oxidative pathway, but it's usually more effective to treat them in the field using a reductive pathway. Not all activation methods give you both pathways. For example, the iron chelate or Klozur 1, which is a mixture of 3 different activation methods, are blended into Klozur 1. All of those activation methods typically just give you the oxidative pathway. So they can be used to treat your chlorinated ethenes or your petroleum hydrocarbons and those types of other compounds that react via the oxidative pathway. With a very brief introduction to the chemistry, I wanted to transition to a couple of quick pilot studies. These are both up on our website, so if you'd like to have more information, please go to klozur.com or evonik.com, or actually peroxychem.com is still active, but soon we will be transitioning over to Evonik active oxygens. But you'll still be able to go to klozur.com to find our information. So the first site is a former industrial facility in Germany, where Klozur KP was used to treat a combined mixed plume of CVOCs and BTECs. I wanted to just highlight this data, but as you can see, Klozur KP was activated with iron chelate, was very effective at treating all of these compounds. All of these compounds we know are treated via the oxidative pathway. At the 6-month mark, your PCE, TCE, were both treated by up to 3 orders of magnitude or greater than 99% reduction, but even your PAHs and some other compounds were treated by 94.5 up, 92.7% reduction. The application was a pilot application, and it was in the middle of an industrial area. And 12 months post, you can see that the PCE and TCE treatment persisted, staying at greater than 99% reduction. However, we did see what I consider to be recontamination, not rebound, but recontamination of the DCE, BTECs, and PHs. And I say recontamination because basically this small pilot test area was recontaminated by upgrading groundwater. And that's what we saw with the DCE, BTECs, and PAHs. This is one of the things it's important to monitor for a variety of different analytes, including sodium, potassium, and sulfate, so that you can actually watch upgrading groundwater migrate into your target area and evaluate whether or not you're dealing with rebound or recontamination. Another quick case study was an ERM site in the Pacific Northwest. Here, Klozur KP was used to remediate pentachlorophenol, where ERM was evaluating a property boundary PRB. In the pilot study, they injected Klozur KP activated with hydrated lime in a cross formation, and they had 3 primary monitoring wells that were clusters. So there was a shallow monitoring well and a deeper monitoring well. And then there was a monitoring well that was also in the monitoring program. However, we weren't necessarily anticipating seeing beneficial treatment 35 feet down gradient. Starting with monitoring well 1, first the baseline contamination was observed to be very low. As sometimes happens when you go out in the field with a pilot test area, the contamination is not always what you had anticipated. But even starting with these low baseline concentrations, by a 4-month mark, you were looking at greater than 99% reduction in 1S, and you were seeing significant reduction in monitoring well 1D as well. Starting with monitoring well 2S, you started to see much higher baseline contaminant concentrations with 1,700 micrograms per liter of pentachlorophenol. And you can see very quickly at the first monitoring point, 6 weeks later, you were looking at greater than 99% reduction. And this persisted over the entire 5-month monitoring program. Monitoring well 2D, which had less contamination, was non-detect by the 6-week mark. Moving to monitoring well 3S, you started off with 2,000 micrograms per liter, and by the 3-month mark, you were looking at 99.9% reduction, with that 2,000 micrograms per liter being reduced to 1.7 micrograms per liter. Even though it didn't start with as high as concentrations, monitoring well 3D was remediated down to non-detect by the 4-month mark. But what also caused, so all of this was considered to be a very successful, really what we would be anticipating, that Klozur KP could be applied and it could be active for an extended period of time, continuing to treat groundwater as it fluxed into this pilot test area. But what also caught our attention is that 35 feet down gradient, we started to see very beneficial impacts at DGW. And this can be illustrated by the 3-month mark, where the 9,700 microgram per liter pentachlorophenol was reduced to 330 micrograms per liter, or by 97%, with a maximum reduction observed at DGW of a 99% reduction. So in general, we just wanted to summarize, those case studies are on our website. You can go to our website and get more information. And they're pilot tests, and there have been full-scale applications of Klozur KP, but we just wanted to use them to illustrate that Klozur KP has been used to remediate a variety of sites, both looking at source zone treatment and in a PRB type of formation. It has been successfully used to remediate a variety of contaminants, from petroleum hydrocarbons to CVOCs to things like pentachlorophenol. And it's also been used to remediate commingled plumes, including 1,4-dioxane with PCA, DCAs. Treatment has been very good at a number of our case studies, as we just showed with those previous applications. Hydrated lime is the most common activator, resulting in alkaline activation, but iron chelate has also been used. The caveat that we would include with using iron chelate to activate Klozur KP is, whereas Klozur KP is going to persist for an extended period of time, iron chelate is going to be dissolved and it's going to migrate with your groundwater. So if you're going to have treatment that is going to persist, or if you want treatment that's going to persist for longer than a single pore volume to flush through, you might want to go with a solid state extended release activator such as hydrated lime. But if you are going to go into, say, a source zone application where you want your Klozur KP to be, or if you have very slow moving groundwater velocity where your Klozur KP may not persist beyond what one groundwater flush would be, you can, and people have used iron chelate activation. So one of the things I want to emphasize here, and I talked about this during the chemistry when I talked about the persulfate anion being released, is really the remediation chemistry of Klozur KP and Klozur SP. It's the exact same. They both dissolve to form and to release the persulfate anion. So what is really different is the fact that you have the low solubility Klozur KP, the high solubility Klozur SP, and that is, and the time at which they slowly dissolve, or they dissolve. So why Klozur KP? Why would somebody choose to use it over Klozur SP? And it really gets down to time. Klozur KP can sit there and slowly dissolve over an extended period of time, maintaining a consistent concentration. So that's the characteristic of Klozur KP, that low solubility. Whereas Klozur SP, it's going to be dissolved. It's going to be, you're going to be injecting a liquid solution or soil mixing a liquid solution, and it's going to be available at the time of application. And where this becomes critical is that Klozur KP, the crystalline Klozur KP, can sit there and persist in the subsurface for an extended period of time and slowly dissolve to release the persulfate anion. But the persulfate anion in Klozur KP, it's there as soon as you inject, as soon as it hits the water and dissolves. So Klozur SP typically has a reactive window of 2 to 8 weeks, sometimes a little bit longer. To illustrate this effect, this is actually one of the graphs from the original launch webinar of Klozur KP. And in it, this is a column study. This represents a column study where we had about 300 grams of each of the products in a upflow column reactor. And you can see Klozur SP, all of the reagent dissolved very quickly, spiked at near its theoretical maximum, and then it came cascading down. It wasn't perfect plug flow. You can see a little bit of a tail there at the end, but it essentially was and behaved like a reagent that was would in a plug flow reactor. Whereas Klozur KP sat there, the same mass of Klozur KP sat there and slowly dissolved over months and up to 180 pore volumes, slowly dissolving, maintaining 17 grams per liter. So this is the contrast. This is your choice as a design engineer. You can go in there and have all of your reagent readily available, which is great for source zone treatment of highly contaminated sites. Or you can have a reagent that slowly dissolves over a period of time, maintaining a consistent concentration. So what does this actually look like? And this is a table, just to really walk you through this table. We're looking at two of the major factors that determine how long Klozur KP will persist, and that is temperature, and really it's groundwater flux, but I've represented it here as groundwater velocity. To convert it to groundwater flux, we've assumed a 15% effective porosity. But you can see here, if you have, say, a groundwater velocity of 50 feet per year or 15 meters per year, and you have an aquifer temperature of 10 degrees Celsius, you're going to persist for, or we would expect Klozur KP to persist for up to 48 months, or this application of Klozur KP, which is 4 years. If you have a groundwater velocity of 100 feet per year or about 20 meters per year, 20 degrees C, you're going to persist for about 15 months. This application, 1% Klozur KP weight to weight with the soil, it's going to persist for 15 months. However, you start getting into rapid groundwater velocity sites, say 500 feet per year, that same 20 degrees Celsius temperature, you may only get 3, maybe 4 months of persistence, which it's just a characteristic. It's not good or bad, and we'll talk about how that might be used. But the bottom line is slower groundwater velocity sites, lower groundwater flux sites, lower temperatures, KP is going to persist longer, or is expected to persist much longer. So how can this be used? How can you use time to, the time that KP gives you to treat contaminants? Well, one of the areas that we're seeing this be used is to treat aqueous phase contaminants. And I know everybody will first jump and say all contaminants are aqueous phase, but there are contaminants, there are instances where you are primarily dealing with the aqueous phase, such as permeable reactive barriers, and then source zones that are dealing with contaminants such as 1,4-dioxane, MTBE, vinyl chloride. Those contaminants are specifically, because of their low KOC, are primarily in the aqueous phase. There's also times when you want that extended contact time because of either the contaminant or the soil type you're in. Like a low permeable soil is going to benefit from an extended release oxidant because it allows more time to diffuse in. Low solubility contaminants like PAHs or PCBs, and then trying to achieve low remedial goals with low contaminant concentrations, that longer contact time can again be very beneficial. And then finally, you actually can, there are reasons to use Klozur KP in high groundwater velocity sites, and we'll talk about each of these instances. So first, not all contaminants behave the same in the subsurface. I think we all know that, but this is just talking about that a little bit. Specifically using 1,4-dioxane, which is commonly commingled with 1,1,1-TCA and its daughter products of DCAs and DCEs, you can see just looking at their partitioning, the KOC, and these are parameters, are values taken from an EPA document, using an FOC of 0.5% and using the formula that you see at the bottom. The 1,4-dioxane is expected to be 70% in groundwater and 30% sorbed to soil, the organic matter on soil, whereas TCA is almost the exact opposite. 73% is expected of the mass is expected to be sorbed onto soil, and only 27% is expected to be in groundwater. And this leads to a very different type of application, because you're trying to, with TCA, you're trying to treat what's on soil. With the 1,4-dioxane, you're trying to treat what's in groundwater. That's where your contaminant mass is. And you can go through the list, and of course, every compound is going to be different, and actually even the KOCs, you can go out and you can find a variety of different sources that might give you slightly different numbers. For example, 1,4-dioxane, I've seen it anywhere from 2 or 3 up to about that 17 value that is reported here. But you can look at dieldrin that has 21,000, and that's basically sorbed onto soil. Very, very little of it is in groundwater. So this leads to a fundamental concept in remediation. If you have something that is in the aqueous phase, to establish contact, it's going to be easier for that aqueous phase contaminant to migrate to a solid state, an immobile Klozur KP. So if you were to go after an aqueous phase contaminant with an injection strategy, for example, a liquid injection strategy, you're going to be displacing at least a portion of the aqueous phase, and you're going to be dependent upon in situ soil or in situ mixing, subsurface mixing, to get the groundwater that has the reagent to mix with the groundwater that has the contaminant. Permeable reactive barriers benefit from this whole strategy of treating something that's in the groundwater, because the groundwater is migrating towards the barrier. These will have to be periodically refreshed, and you can see from the previous table, it might be every year, it might be every 4 years, but that's going to depend on your site conditions. But basically, you can treat the groundwater before it moves off site or moves down gradient as it passes through the PRB. But you can also treat these source zones and groundwater plumes, various contaminants like 1,4-dioxane, vinyl chloride, MTBE. These have the lower KOC, so they tend to be in the aqueous phase, and it tends to be easier to go in and emplace through fracturing and other emplacement strategies a significant amount of Klozur KP to treat these contaminants. And again, even though it's not a PRB, within that source zone, have those contaminants migrate to the Klozur KP. Longer contact time. So basically, treatment time is not just about kinetics. The sulfate radical and the hydroxyl radical it's well established that they will treat PCBs, PAHs, all of these different compounds. The rate of reaction, once you have a radical, really is not an issue, but you still have to have enough time for those contaminants to desorb off the whatever material they're sorbed onto, the organic matter in the soil that they're sorbed onto, and be available for reaction, to be available for the sulfate radical to react with it, or the hydroxyl radical to react with it. So what that means is that for these compounds that are really strongly sorbed onto soils or have a very low solubility, you want to have a longer period of time, and a time when your oxidant is very active and available to react with them once they desorb and dissolve. So basically, Klozur KP can give you this extended contact time and period of time to treat these PAHs and PCBs. And this is a result that just 56 days. I suspect had this gone out longer, we would have seen even better treatment. But Klozur, same amount mass of Klozur SP with Klozur KP. And you can see with 1254 PCBs, Aerochlor 1254, you got significantly better treatment with the Klozur KP on this bench study than you did with the Klozur SP. Again, slow, consistent treatment as the oxidants there to react with the contaminant as it desorbs versus available all at one period of time. Longer contact time can also be used to treat both low permeable soils and get to lower contaminant concentrations. And this is all about matrix diffusion. So with low permeable soils, the Klozur KP can sit there, and it allows for a longer period of time for the persulfate anion, once dissolved, to diffuse into the low permeable soils, but also allows for a longer period of time for the contaminant from the low permeable soils to diffuse into the fractures, to diffuse into where the Klozur KP is. This is just longer time because that process is the limiting process. That diffusion process in and out of the low perm matrix is the limiting process. So more time gives you better overall treatment. This is also true when you're going after lower contaminant concentrations. Klozur SP is phenomenal at going in and treating, higher contaminant concentrations because, it's easier to establish contact. But once you start getting into the part per billion level, establishing contact is more difficult. So having something that's going to persist there longer is again going to allow more time for things to back diffuse out of the matrix, or the reagent to diffuse into the matrix and get every last molecule, the part per billion levels of the different contaminants of concern. And then finally, I also wanted to talk about high groundwater velocities. High groundwater velocities, the real question is does Klozur KP have a place there? And the honest answer is that, yeah, we are finding that it does have a place. If you think about a 500 foot per year groundwater velocity, that's 42 feet per month or 10 feet per week. And if you are going to inject Klozur SP, which will tend to persist 2 to 8 weeks, that means for every week it's moving down gradient, that it's active, it's moving down gradient on you. So your say your top 20 feet of your target interval may only see the Klozur KP for 2 weeks of contact time. So a lot of your active oxidant, if it's active for say 8 weeks, you're only seeing treatment for 2 of the 8 weeks that it's going to be active. Thus you can get some incomplete treatment because your oxidant was only in your target zone treating and contacting your soils for 2 out of the 8 weeks that it was active. Whereas if you went in with Klozur KP into a high groundwater velocity zone, you could inject it, say it was 500 feet per year, 20 degrees Celsius, it would persist for 3 months. It would slowly be dissolving in this high groundwater velocity zone, releasing the persulfate anion, and you would have that contact time in that interval for 3 months rather than just 2 weeks. So yes, there is a place for Klozur KP in high groundwater velocity zones. So just talking about the conceptually where we're seeing Klozur KP being used, I also wanted to talk a little bit about the lessons that we've learned over the last 5 years. One of the big ones is, of course, monitoring. Klozur KP, you need to have monitoring wells in the injection area, in the permeable reactive barrier area. Of course, performance is expected to be best at the PRB, within the PRB, and that's really where you would expect to see the best treatment, rather than just using downgradient monitoring wells to look at the performance. Of course, those are important too, but as we've seen in other case studies, you typically see the best treatment within the PRB and then diminishing treatment as you move down gradient, at least in early time frames, such as what you typically use in a pilot test of, up to say 6 months. The other reason to have a monitoring well within the PRB is, of course, that monitor for the activity and the persistence. So not only are you going to see the true effectiveness of what the Klozur KP can do, you're going to be able to monitor to see is the activity of it diminishing? How long did it really persist? Which is something that you're not going to see if you do not have those monitoring wells within the pilot test or within the PRB or the injection area. So just talking about a PRB formation, for example, we recommend putting monitoring wells both down gradient, at staged areas, say, like 9 feet down gradient, 10 feet down gradient, 30 feet down gradient, but also within the PRB. And in source zones, we recommend putting in monitoring wells, both, again, down gradient where you want to see the effect, but within the injection area. We also encourage people to monitor for the expected residuals, potassium, sodium, calcium, sulfate, things that we expect to, be remaining after the reaction has occurred. Residual persulfate, pH, conductivity, and ORP. This allows us to, evaluate whether or not something is, whether there's rebound occurring, recontamination occurring. We can look to see if and when upgrading groundwater has flushed in and has moved these residuals out of the area. It just basically helps us understand, when you're doing subsurface remediation, it's not a static system, it's a dynamic system. By looking for all these residuals, you can better understand what is occurring at the site. In terms of site characterization, having accurate data on parameters that will help you estimate groundwater flux is critical. Most important is a good groundwater gradient, both understanding the direction and the actual gradient and hydraulic conductivity. I worked with one pilot test where they had down gradient wells and never saw the sodium, never saw the potassium, never saw the sulfate, indicating that there was likely a side gradient going on at that site. Effective and mobile porosities that can be used to better understand the differences between going from groundwater flux to the actual groundwater velocity. So that's another parameter that would be best to have actual site data on rather than just using assumed values. And then the application. Klozur KP and hydrated lime, we started this and we thought they were going to be applied maybe 30%, maybe 35%. But in actuality, and FrX will talk about this, we're seeing contractors go out at 50 to 70% by weight. So these are two reagents that can be combined together and actually injected at very high concentrations. And then also we would absolutely encourage care with the fracture pressure and the injection volumes to control distribution. You don't want to over-inject into certain fractures that will lead to distribution outside of your target interval and target area. So those are two key parameters. With that, I just wanted to quickly summarize before handing this off to FrX. The Klozur KP has the same powerful chemistry as Klozur SP. They both dissolve to release the persulfate anion. They both can give you, depending on the activation method, the oxidative and the reductive pathways that can lead to the treatment of a lot of different contaminants of concern. The main difference is having all of the oxidant available instantaneously with Klozur SP, or having that oxidant potential available over a period of time as it slowly dissolves with Klozur KP. This extended time with Klozur KP, we're seeing people use it for permeable reactive barriers, to treat aqueous phase contaminants, to go after contaminants that have a low solubility or a high KOC, go after low permeable soils, and go after sites that have very high groundwater velocities. So with that, I will transition this over to Drew and Chapman.
Hello to everyone. This is Drew Baird with FrX. I am going to get right into it because we have a lot to cover. So what we're going to talk about today is hydraulic fracturing of Klozur KP slurry. And FrX began doing this back in 2017. We're going to talk about our experience, and we're going to start with some principles. So fracture form, because it's so important, we're going to talk about it. plus a little bit about the hydraulic fracturing process. We're going to talk about distribution mechanisms. Once you have KP slurry in these discrete fractures, how does the persulfate and the activator, if applied, get into contact with contaminants? We'll talk about that, especially for low perm settings. And then we've got a lot of data. Chapman Ross, my colleague, is going to be presenting a lot of these data. It's going to include where we've done the work and some statistics on that, plus reagent loading and field productivity, daylighting, costs. And then I'll come back in and talk about a KP case study at an industrial facility in New Mexico. And then we'll have a Q&A with Brant, me, and Chapman. All right, so those of you who have seen an FrX presentation before have undoubtedly seen me present this slide because it's so describes or represents fracture form. And what you're seeing here is a trench that's been excavated in very low permeability glacial clay till, 10 to the -7th, 10 to the -8 centimeters per second. And these three features are fractures, one at about 3, 5, 7 feet BGS. We've got a white line here that's a string as a horizontal datum. And note the regularity of the fractures, meaning that they are horizontal sheet-like structures, in this case with an approximate injection radius, fracture radius of 10, 12 feet. We often use 15 feet now as a common design metric. These things are, in this case, filled with coarse sand. That scale is centimeter scale, so they're about a centimeter in aperture. There is, and you can see it, variability here. We're going to be talking about KP instead of sand. But you've seen us present fractures in trenches, and this is a fracture cutting across relict foliation in a former metamorphic rock, now chemically weathered in place to form saprolite. There's a quarter, US quarter for scale. So we've done over a dozen of these inject and then excavate, which has taught us a tremendous amount about fracture form. On to the process, and this is very simplistic, but the first thing you do is create a thick slurry with KP, and in this case, hydrated lime. And what you're seeing here, obviously, is a very thick slurry. That is 65, probably closer to 70% solids. That's KP plus hydrated lime, percent by weight. So 65 to 70% solids by weight for that very thick slurry. Next, what you do is you pump the slurry into the formation. And when you do that, none of that slurry, and this is true of all slurries, when you pump a slurry into the formation, it is not going to be able to fit through the pore spaces, the pore throats. So you don't get distribution like you do liquids, obviously, but what happens is you build up pressure into the formation and you make a crack. And when done in a controlled way, that crack, that fracture, is a horizontal sheet-like structure. And one thing I want to point out that may not be obvious is the process of injecting the slurry simultaneously creates the fracture. It's sort of a tensile splitting of the formation, and that slurry fills the fracture as it's created. And then we monitor injections and record process data, which I'll show you some of that. On to distribution, visually it's best illustrated with potassium permanganate, which you see here in this photograph. There's a potassium permanganate fracture there in the center of the CPT core, and you can see very clearly that vertically, which is to the left, upward, and to the right, downward, you get penetrative, diffusive transport of aqueous permanganate from that potassium permanganate filled fracture. So this is fine-grained alluvium. You can't see it because aqueous persulfate is colorless, but the same process, the same principles apply. Diffusion is going to dictate a lot of distribution of aqueous persulfate from the fracture. And there's been a lot of research and documentation in peer-reviewed journals on oxidant diffusion via chemical oxidant distribution via chemical diffusion. You don't have time to read all these. This, like other slides, are going to be presented or saved as PDFs, and you can go through details at your leisure. I'm going to hand things over to Chapman in just a sec, but I just want to finish this part of the presentation by pointing out that these blue dots are FrX chemical oxidation projects since our founding in 1994, 2,000 projects represented by about 100 sites here. And with that, I am going to pass things over to Chapman, and I will, Chapman's going to start by talking about KP specific projects. Chapman?
Thanks, Drew, and thanks to Brant and Jen for having us here, and FrX and Evonik for hosting. So Drew showed you all those sites where we've done, those 95 sites where we've done ISCO injections. As Brant pointed out, KP is a newer technology. It was announced in 2016. FrX did the first KP injection in the US, and that's what's shown here in 2017. You can see that green star. If you can go ahead and step forward, Drew. Our largest KP injection project down in Florida, 194,000 pounds of KP, 234 fractures. That was for treatment of 1,4-dioxane. Over in New Mexico, and this is the case study that Drew is going to talk about in a little bit, we had 2 phases of work in 2017 and 2019 where we injected a total of around 40,000 pounds of KP SP and the activator into 71 FrX. Keep going. True. Yeah, and then 2 more projects, one in 2020 and another in 2021, both full scale, and we will talk a little bit about those projects when we talk about the numbers. So let's talk about the numbers. So I want to talk about reagent loading. I want to talk about mass loading of KP in terms of how much soil there is in the treatment area. And I want to talk about productivity. How much of this stuff can we put in the ground in a given day? Because all these things fit together. So you can see the pounds per fracture there in the 3rd column. So we are able to put, and by using such a highly concentrated, a heavily loaded slurry like Drew showed earlier, that video, that toothpaste, if you will, like consistency, we're able to put in 5 to 830 pounds of KP, an activator per fracture. So that allows us to then apply a lot of KP to the formation in a day. And you can see there on the right-hand column, 3,000 to 6,000 pounds per day of KP applied to the formation. That is a lot of material being put in the ground. And the result of loading those fractures up and putting that material in the ground quickly and in a controlled fashion allows us to achieve the sort of mass loading that you're seeing in the 2nd column here. So in general, most of these fall in the 0.2 to 0.3% range. We've got that site at the bottom there, the New England site that was performed just this year. That mass loading is around 0.7% by dry weight of soil. However, based on some recent injection work that we've been doing and an analysis that we've undertaken with PeroxyChem and conversations with Brant, we believe that we can achieve up to 1.25, 1.5% mass loading by dry weight of soil, and we anticipate doing that in the future. That, as Brant pointed out, there's a time component here. The more of this material we can put in the ground, especially into these low permeability formations, the longer the material can stay active and work on treating those tough low permeability formations where we've got that matrix back diffusion working against us. Next slide, Drew. So we in order to achieve those types of mass loading, those loading rates, we got to keep the material in the ground and we got to keep it in the target injection zone. Here's a great picture from that was kindly provided by Tom Fox that works for the state of Colorado. This shows all the things that can go wrong with an injection program. Here, I believe Tom was showing an activated carbon slurry, but any slurry can cause these types of problems. Go ahead, Drew, in advance. So these big fractures that you see reaching out and coming to the surface, that's indicative of a steeply dipping fracture, an uncontrolled hydraulic fracture, we call it. Next slide. Yep. And there are a lot of different ways that this can happen, but they're generally man-made. They're generally operator error, and we believe that and that these can be prevented. Of course, if you get too many surfacing events, if you can't keep the material in the ground, that can really kill an injection project. That can cause a lot of problems and send you home, or maybe you don't get the next phase of work. So that's what we want to avoid. And how do we avoid that? So let's go to the next slide, Drew. Well, as Drew pointed out, we use a thick, viscous slurry. FrX has a bunch of methods to then direct that slurry in a horizontal direction. Next. And one of the key pieces of putting that slurry where we want it is controlling the volume of injectate and controlling the pressure. So here's a pressure log from the New Mexico site. This is the case study that Drew's going to talk about. And what I want to bring your attention to here is the maximum pressure at most of these fractures. So each of these little blips on the radar, if you will, are fracturing events. And we've got, in general, the pressures for these fractures around 90 psi at the maximum. So that's a pretty low fracturing pressure. That's where we want to be to control these fractures. We only have one fracture on this particular day. All these fractures were performed in one day, where we jumped up to around 150 psi. So pressure is a very important key element here to controlling the fracturing process. So let's put our money where our mouth is. You say you can control surfacing events. Well, how do we do? So here are those 4 projects, 5 if you count New Mexico as 2 projects, those 2 phases in New Mexico. So over those projects, we did 363 fractures, and we saw daylighting or surfacing, whatever you want to call it, at 5%. In 5% of those fractures, only 11 daylighting events in those 363 fractures. And I will point out specifically here, the Alabama project, where we were injecting, all the fractures were done between 4 and 8 feet below ground surface. That's not a typo. Those are very shallow fractures and very challenging to keep the material in the ground there. However, we were able to limit the surfacing to 13%. We only had 5 daylighting events and 40 fracs. And the client was very pleased with that. So that brings us on to cost. So we talked about mass loading. Let's talk about cost. Everybody always asks about cost. So here it is. This will give you a sense for really the overall project cost to implement Klozur KP type treatment with FrX at a site. So this includes drilling, it includes the fracturing, our injection services, as well as the KP and the activators. I talked about these overall amendment masses before. I'm not going to go through that again, but I will bring your attention to the treatment areas to give you a sense of the scale of these range of projects. And they range from 1,300 square feet on up to 48,000 square feet. So a pretty big range of size in terms of the treatment area. And then cost. So the all-in treatment cost for the top 3 sites there is $54 to $84 per cubic yard. That bottom, a New England site, the cost there was around $222 per cubic yard. That's an interesting site. It's a very small treatment zone. Lots of logistical challenges at that site. So I'd say that one's a bit of an outlier, but we wanted to put it on there to give you a sense for what how high the costs might get. And that will bring us into the case studies. I'll pass it back to Drew to talk about the New Mexico case study, which I mentioned earlier.
Great, thanks, Chapman. I'm going to go through this really quickly because in 2 minutes I start cutting into Q&A time. So I want to thank Jacobs for allowing us to share this information on an industrial site in New Mexico. It's a fine grain treatment zone but with some carbonate rubble, which transports groundwater in that rubble, those rubble zones very quickly, which is an added complication. We're dealing mostly with naphthalene, benzene, and 1,1-DCA, and I'll come back to that in a second. So there has been a long-running program of remediation for the source and plume based on a variety of factors. What we're going to focus on is a source area that had undergone SVE after some soil excavation, yet MW12 remained above limits, stubbornly so for all three compounds. And you see all of this variability, this what I call spikiness, in my experience is an indication of nearby residual mass, possibly NAPL, but not necessarily, could be just heavy sorbed mass. So that's what we were targeting. So for our presentation, or for our project, it was a two-phase project, and I got this information from Mike Perlmutter and Elisa Forsberg, in part from their Battelle 2018 presentation, as well as conversations and all that. The approach was ISCO in the source, and it was a phased approach. And then far down gradient, there's some hydraulic control that's been in operation for a while. And then there's a plan in place to polish a source with enhanced reductive dechlorination by adding an electron donor. And that's because, as Grant noted earlier, you know, DCA usually has a weak oxidative pathway, but there's a reductive pathway. And of course, that can be accomplished chemically, but the plan here is to do that biologically as well. So some of the decision points involved around that MW12 area, in the source area, characterized it with a lot of direct push injection locations, soil and groundwater sampling, did treatability testing to determine proper activation, and then executed phase 1 to be followed, if necessary, with phase 2. So you see the two areas here. 2017 was focused, it's down gradient, groundwater's flowing up and to the right, and there's MW12, and that's the 2017 injection area, thinking that, okay, we might be able to knock out this source without doing a larger project. You'll see some results that indicate why in 2019 there was an additional injection up gradient to get more of that source area. You're going to see data from MW12 as well as 3 other wells starting now. MW12, here's the chart, and I just want to put, you know how to read charts. The 2017 injection here on the left in dashed, 2019 injection here in solid, and you're looking at DCA, benzene, and naphthalene, plus the cleanup goal for 1,1-DCA in New Mexico. You see the MW12 saw in all compounds a very quick reduction in COCs, and then rebound. Which we've all seen in ISCO, indicating that there was more residual mass up gradient, a second treatment, and naphthalene and benzene are taken care of, and we are trending downward below the cleanup goal for 1,1-DCA. MW36 over here was not installed. 36, 37, nor 38 were installed at the time of the 2017 injection. So they were installed and then sampled shortly before the 2019. You can see the obvious trends there. On to 37, you see the trends there, and we're trending and are currently below standards for 1,1-DCA. And 38 remains the only well where we've got one constituent, 1,1-DCA, above goals. You can see there's an obvious trend down, followed by a little increase. So there's a lot going on there that could be chemical and biological mechanisms in place, or treatment mechanisms going on. And again, there's a plan to inject electron donor to polish off this residual 1,1-DCA. So a successful case study, and that just sums up one of several case studies that me and Brant showed that demonstrate the versatility and successful application and just the capabilities of Klozur KP. Powerful oxidant, excellent longevity, very versatile in terms of contaminants treated and geologic settings where it can be applied. Oxidant distribution from KP filled fracs is very well understood. Good fracture form is paramount, and it can be done with a good understanding of the principles of fracturing and the application of proper techniques. Chapman showed you how daylighting can be minimized or even eliminated. And high dose delivery of activated KP in low K units is most of those sites were low K treatment zones. And we're getting in, 500 to 900 to 1,000 pounds of combined KP and activator per fracture. And we believe with good reason that we can increase that, and our next project is likely to increase that. And then you saw the treatment costs, total project costs, basically everything but the consulting time is typically less than $85 a cubic yard. So good costs there for source area treatments. Just thank you to our audience and also to our hosts, Jennifer and Brant at Evonik. This was a lot of fun.
Yeah, thanks guys. We really enjoy working with you and appreciate the opportunity.
You bet.
Well, we appreciate the collaboration.
Baird for bringing your expertise to our webinar series. Okay, thanks everyone.